And speaking of exams, we've got one of our own coming up on a week from today, Thursday the 5th. And so for that exam, you can prepare an equation sheet, like I was saying in the last lecture. You can prepare a formula sheet, and in fact, you can have solved examples or a description of your workflow to do certain problems on that if you like. You should bring your laptop both days next week. On Tuesday, we're going to use your computer for doing some example calculations related to infiltration. And then on Thursday, you'll need your computer for the exam. There will be a question, at least one, where you need to have your laptop available. And it should have an internet connection too. So if you sometimes have trouble connecting to the Wi-Fi network or something like that, maybe get it sorted out before the exam on Thursday. Any questions? All right. Well, in the last class, I told you that what we're working towards is a conceptual model for how much of the precipitation ends up as runoff. Because as hydrologists working with engineers, our primary focus is in quantifying the peak flow rate that has to be accommodated by engineered structures downstream of a watershed. So we're trying to give the cue to the engineer who's going to be sizing a culvert. Or we're going to be giving the flow rate to the engineer who has to build a bridge at a certain elevation over a stream. And so a conceptual model says if we have a certain amount of precipitation, what are the losses going to be? There's all these little places that the water goes before it actually ends up concentrated at an outlet, causing peak discharge. And so one of the largest fractions of where the water goes is as infiltration into the soil. So today we're going to be talking about soil, and it's kind of ironic because I did worse in soil mechanics than any other course in my undergraduate career. It was my lowest grade. And now here I am talking about soils today, so we'll see how it goes. Now, a lot of the variation in behavior that we observe in hydrology arises out of differences in the characteristics of soil that's related to the size of the particles. And so we all know that clay is special, right? Clay is really special. It has a low hydraulic conductivity, and it holds on tightly to moisture because the particles themselves are so small. And since clay particles are small, they end up having a charge on the outside. It's a negative charge. Electrostatic forces that will tightly bind to the water that's adjacent to those soil particles. Now, in contrast, soil particles are relatively large. And this illustration is actually important because it shows not only is there a variation in soil grains for sand, but there's also a variation in the pore size. And so look at some of these voids are really large. And maybe it would be a misnomer to talk about the diameter of that void because it's not circular in shape. But it's useful if we approximate this void and it's connected to another void. This is just a cross-sectional view, but think about this in 3 dimensions. There are these circuitous routes that go from the surface downward, and some of the routes have very small diameters, meaning that it's these tiny little voids where there's a small void to begin with and then maybe another fine-grained sand particle in the middle of that, and so we end up with an even smaller void. And so there's a wide distribution in the size of the voids. And so there are some routes from the surface to the bottom that are maybe predominantly large diameter voids, and some routes from the top to the bottom that are really small. And of course, they're not exclusive. It's not like there's only one path from a certain location at the top downward. There are branching voids. But we're going to look at the effect of that distribution of void sizes and how it actually changes the way that water infiltrates from the surface down to the saturated zone. So the primary way that we're going to be modeling the relationship between soil and water is as a function of the affinity that soil has for water. And we're going to measure that as suction. And it's partly about wetting the surface of these these grains, and it's also partly about maximizing contact with the voids, and that's related to the capillary effect. You may remember our discussion of the capillary effect in fluid mechanics and how water can rise upward through a small diameter tube. All right, so you already know that soil is a mixture of components, and so it would be uncommon for you to have pure sand or pure clay over a large watershed. Now, there may be individual locations that are predominantly one thing or another, but more usually it would be a mixture of different properties, a mixture of different components, and therefore taking on a mixture of those properties. And there are maps that we can download online that will tell us about the soil characteristics of a watershed. And what we'll actually do is, when we get to what I consider the pinnacle of the course, where we're putting together large-scale watershed models, we'll download that soil data directly from the USDA. The United States Department of Agriculture actually is the federal government office that is tasked with putting data out there about what the soil characteristics are. And they're amazingly fine detailed maps that are based mostly on topography. They're not based so much on a guy who went out into a field and dug a hole and saw what kind of soil was there. They do a little bit of that, but then based on measurements at certain key locations, then they'll extrapolate the soil properties all over a wide area. You know, they'll say, we found in a 10% slope on a south-facing area that it was predominantly this kind of clay, and then they'll say all the locations that share those same characteristics, we're going to assign the same kind of clay. And then in hydrology, one of the most important soil characteristics that we are interested in is the capacity for infiltration. And they'll correspond different types of soils to how quickly the infiltration occurs. So it's these mixtures of soil that eventually we'll be getting GIS data for and using it as an input for watershed models. So at any one of those locations in the GIS model, we'll be able to click on the map and it will tell us what kind of soil it is, and then based on the USD classification, there may be a breakdown of the percentage of each of the three soil components. All right, so through today's lecture, we're going to be looking at a lot of really great figures from the textbook. My only complaint with these figures is that they're presented in kind of a strange order. And I've tried to rearrange the order from the order that they're presented in the textbook, and I'm not sure if I've done any better. It's just sort of like all of these interrelated figures that kind of make the same point, and they're definitely worth looking at each individually, but it's kind of a Gordian knot knowing where to begin. So you'll remember porosity, and these are in bold. Each of these next few terms are terms that if you don't already remember, you maybe want to refresh your memorization ability of. Porosity is the pore space relative to the total volume. So if we go back to this figure, if I was to draw a square, it may be a 1 millimeter square, and turned it into actually a cube, a volume of 1 millimeter, then we'd want to know within that 1 millimeter of cubic volume, then how much pore space is there relative to the overall volume. And the reason why that's important is that that pore space is going to be filled with something, and in the saturated zone it's filled with water, and even above the saturated zone it's partly water that's occupying that space. And what we can see, the trend of porosity is there is a range of typical values depending on the soil, but you have increasing porosity in the direction of coarse grain materials working towards fine grain materials. And so clay are those really small particles on the right side. On the left side, sands are more coarse grained, and so it's a little bit counterintuitive if you think about it, because at least in my mind, it would make me think that you would have an easier time packing in the voids with actual soil grains if the materials all themselves were small. But this is saying that's actually the opposite, that you have more pore space for fine grain clays than you do for the coarse grained sands. All right. Now, here's another definition that we need to think about because it's related to how much water can be in the soil between rainfall events. The field capacity is if we have a certain sample of soil and we just use gravity to drain it out. So we're not baking it. We're not trying to extract moisture out of the soil with plants, but it's simply just drip drying, in other words, drip draining. So a few days after precipitation, the field capacity is how much moisture is there in the soil after a recent storm event. And again, the trend is increasing field capacity as the particle size gets smaller. And finally, wilting point is a measure of how easily plants can extract water from soil. And so it's how much water has to be there so that the plants don't wilt. And I think of it this way, is that you have to have more water in clay than you do in sand in order for the plants not to wilt, because the plants can extract the water from sand more easily. You know, clay particles are holding on to the water with quite a bit of force because they're really highly charged because of their small size. And so clay wants to keep the water, and so it won't give it up to the plants very easily. And so there has to be more water in a given volume of soil for the plants to be able to take it away from clay than compared to sands. So you need a lower percentage of water to satisfy the wilting point in sand. All three of those trends make the same point. The point being that water moves through sand more easily than it does through clay. The direct measurement, of course, is hydraulic conductivity, but each of those other three parameters are important as well. And so we can measure one of the physical properties of soil is the suction in the unsaturated zone that's above the water table. And I guess just as a first look of it, let's say here's the surface, and of course above the surface is air, and there's underneath the ground, here's the water table. And so this is the saturated zone, and here's the unsaturated zone. Now, I always used to be so confused when I'd read newspaper articles that would talk about underground rivers or underground lakes, because sometimes in the popular press they talk about groundwater in ways that would make you think there's like a big cavern under there, and there's like free water, you could go canoeing in it or something, or diving, and it's not that at all. They're talking about underground rivers, but really what they sometimes mean is just that there's water underground in between the soil grains, filling in the voids, and it maybe is moving, which is why they call it a river, is it's just groundwater that's on the move. The unsaturated zone is sometimes also called the zone of aeration, or the vadose zone. When we're talking in environmental terms, sometimes the vadose zone is the term that's used. Down in the saturated zone, that's where the voids are completely filled with water. But even in the unsaturated zone, it's not called the dry zone because there's still plenty of moisture in the soil above the water table. It's just some of the voids are empty. So down in the unsaturated zone, the water is being drawn upwards because of the capillary effect. And here's just an illustration to remind you of the capillary effect, and that is that water is attracted to silicon dioxide. And so if we dip a glass tube down into water, the water will rise up in the glass tube. And you may remember that we actually had a little glass tube that we used in the lab last year in fluid mechanics. And we observed the capillary effect. But it had to be a small diameter tube because the smaller the diameter, it increases the surface tension relative to the weight of the water. So although on this left side there is still more surface tension drawing the water up, the weight of the water grows faster than the surface tension does, because the surface tension is related to the surface tension constant multiplied by some distance. So in other words, the force sigma was some length times the surface tension constant, where the length was just the circumference around the tube. So although this large tube has a longer circumference than the small tube, the area is pi d squared divided by 4. And so as you have an increased area, then the weight of the water grows at the square of the rate of the diameter, whereas the circumference just grows linearly with diameter. So the main point is, if you have a small diameter glass tube, the water will rise. And silicon dioxide is found in a lot of the soils. You know, sand, clay have the same water. Water is attracted to those materials in the same way that it is that glass tube you saw in the lab. And so we can think of this unsaturated zone. Remember, it's all these little routes to the surface. And some of the routes have big pores, and the water won't go up very high through those routes with lots of interconnected big voids. But some of those routes to the surface are a lot of interconnected small diameter voids. And so the water will rise quite high in those locations. So if we take a gauge and there's water inside here, then water will actually suck the water, the soil will suck the water out of the tube as a function of the soil water pressure. And we can measure the vacuum. The water will actually go downward into the soil. And one of the properties we'll take a look at, we've got a figure of the vacuum for the soil water pressure, and it decreases. The more moisture you have in the soil, then the less likely it is going to be drawing water out of this instrument than compared to if it was oven dried, then there's going to be an extremely high vacuum pressure there. So here you can see clays, for example, which are really strongly attracted to water. If they have a low degree of saturation, then there's going to be a really high pressure. And this is a log scale here, just because if it wasn't a log scale, then we wouldn't really be able to see clay and sandy loams on the same figure, because the clay has such an extraordinarily high pressure that it would be like a straight line and then clay. So that's why we've got here the log scale of that soil water pressure. So the trend that you need to keep in mind is that when you have fine-grained soils like clays, then the tension is much higher, and then that tension or soil water pressure decreases with degree of saturation. But even when the water is saturated, there's still an attraction there. There is still some soil water pressure. On average, across the face of the Earth, 76% of precipitation onto the land infiltrates. We had kind of like a global view of the water cycle that we looked at in one of the earlier recent lectures. And it was saying, you know, on a basis of 400 some units evaporate from the ocean, then 100 of those units will fall onto the Earth's surface, and 30-something of those units would run off, and so the rest of it infiltrates. So it's a big fraction of the precipitation that occurs. Less in urban areas, because urban areas increase the amount of impermeable surface. The water in the unsaturated zone is where most of the plants that we rely on get their moisture. And so very few plants will have roots that go all the way down into groundwater. Some trees might, but most crops wouldn't have a root structure that goes down into the saturated zone. The capillary rise is the effect that we'll look at a graph in a minute of the amount of saturation inside the soil. And at the interface of the water table and at the interface of the vadose zone and the saturated zone, it's not like there's suddenly, you know, it's fully wet and then the same amount of dry, it decreases gradually because of the capillary rise. And so we have this infiltration coming down from above and actually capillary rise coming up from below, so that there is a curve of moisture content through the unsaturated zone that's important, because how quickly water can infiltrate partly depends on how dry the soil is before the storm. And so if the soil is really wet, then the movement of the water through the soil is going to be much slower than if it's dry to begin with. Okay, so here's another figure that's going to help us to better understand some of these terms. The field capacity is the one we already talked about, where it's just related to gravitational drainage. And if you look at this figure, what it's showing is that the field capacity is corresponding to a typical pressure head of about minus 340 centimeters of water. And if we had it completely flooded, then this amount of water, the gravitational water, this is like the fraction of water that can be drained from the voids. But I'm such a terrible artist, and this is a subject that really could benefit from someone with great whiteboard skills. But let me just say, all right, we've got a sample of soil, and we've got some soil grains here. Okay, and we've got water in the voids here, and we're going to be removing water gradually due to certain effects. And so the field capacity is the amount of water that's going to come out just through gravitational drainage. And obviously that water is going to come from the largest voids first, because water can move most easily through the large diameter channels. And so I'm just erasing some of the shaded in area to illustrate that some of the water has come out, but there's still a thin layer of water along the exterior surface of the soil grains. Whether they're large or whether they're small, there's still some wetting, and that is the hygroscopic water, the thin layers around the soil particles that even the plants aren't going to be able to extract. So the plants take what's kind of in between, the water that the soil grains aren't going to get rid of. They're not going to, there's more of a suction pressure or an attraction between the outside surface particle of the sand and the water than the plant can even draw it off. But of course, oven drying could get that moisture out eventually, or evaporation through air drying if you took the soil up to the surface and spread it out. But the wilting point is where the plants don't even have enough removal ability to match the amount of moisture that's being lost to the atmosphere. Okay, so here's another great figure that's showing, as we work downward through the soil, the water content. This pressure scale on the right side of the figure is saying, of course, once we get down into the groundwater, then the pressure is increasing linearly at the rate of the unit weight of the water. So the slope of this is equal to gamma as we go down through the groundwater. And as we go up, there's even a linear section inside of the capillary fringe. But then in this intermediate zone, between the root zone and between the capillary fringe, then this water pressure profile and the amount of water that's there depends largely on how recently it's rained. And when we do our watershed modeling later in the semester, we're going to be keeping track of something called antecedent moisture condition, AMC. And we'll do simulations of how a watershed behaves during a rainstorm if it rained 5 days ago, which is kind of like the normal condition, is to assume that your most recent rainfall was within 3 to 7 days. That's the typical. Or if you had rain within the last 1 to 3 days, then the wet conditions are going to give you a different response. Or if it's been very dry, then you'd have another different response. And what we're largely going to be simulating is variations in this pressure profile, and what that means is changes in how quickly and how readily the water moves downward through the soil column. Because if you had a constant pressure profile, if the intermediate zone was fully saturated with water, then the precipitation is just going to pool at the surface, and it doesn't have any suction drawing it down through the soil. But if conditions are very dry, think about, back to this figure, when you have dry conditions beneath the soil, then the water doesn't just flow down due to gravity, but rather the soil is actually sucking it down from above. You know, there's a negative pressure that draws the water from the surface. And so one of the assumptions that we're going to make later on when we try and simulate how quickly infiltration occurs is we're going to assume that there's ponding at the surface, that there's just a continual supply of water at the surface. And that's kind of not a great assumption, because ponding doesn't occur until the infiltration rate exceeds until the precipitation rate exceeds the infiltration rate. So you don't have ponding until the first few minutes after the storm. But the reason why we make that assumption is what's even more important than the depth of ponding at the surface is the moisture content of the soil, because it's going to be sucking the water down through the soil. So this is a profile of pressure, and we're also going to look at a profile of water content that kind of matches the pressure profile. The water table can be perched in some areas, and perched means it's elevated compared to the water table in other locations, and so that's what causes the lateral movement. Water doesn't just only move from above down towards the saturated zone, but it maybe is raining in one part of a basin and not raining in another. And so depending on where precipitation is, that can cause a perched water table, maybe because of variations in where the rainfall is, or it could be due to soil variations. It may be that even if you have even rainfall over an entire watershed, there could be some locations with sandy soils that the water moves more quickly. And so that means that if the water is infiltrating more quickly in one part of the watershed, then the water table is going to get deeper under that soil with a higher hydraulic conductivity. And so then the groundwater flows laterally towards some outlet. And so this is showing base flow towards what maybe is a stream. And of course there would also probably be some runoff at the surface, but streams stay wet through even dry periods because the water moves a lot more slowly underground than it does over the surface. And so that's why some streams will continue to have water in them even through the summer months, is because of the slow progression of water through the subsurface. So the rate of infiltration depends on the types of plants you have. They can affect how deep the water can actually puddle in some spots, the soil properties, and then the condition of the soil surface means that if you are scraping and disturbing the soil surface, then you may decrease the ability for the water to infiltrate there. Just think about if you're tamping it down and you're packing the soil, then you're kind of capping off some of the voids that otherwise would be open to receiving the water. So the saturated zone is beneath the water table, the unsaturated zone is above it, and the soil moisture is going to be increasing. So not all of the precipitation that goes through the unsaturated zone makes it to the water table. So if you have 1 inch of precipitation at the surface, that doesn't mean that the water table will increase 1 inch, because there are a lot of other voids that have to be filled, or the soil moisture may need to be replenished. And so the water table depth changes unpredictably depending on the conditions inside of the unsaturated zone. Okay, this figure is it's showing the relative fraction of where the water is during a storm. And so the way that it works is on the horizontal axis here is time. And if we did a cross section at any slice of time, then that would tell us the relative amount of water in different places, or what the water's doing and where it's going. And so this is just kind of a conceptual approach to where the water is. You wouldn't necessarily think of it as like actual amounts that you'd look up off of this table and use it for modeling, but it's just saying at the beginning of a storm, let's say that the precipitation is occurring, and we're going to assume that a constant amount of the water is being intercepted, which means water is wetting the surface of buildings, or maybe it's wetting the surface of plants or trees before it gets down to the ground. And evapotranspiration, let's just to simplify things, assume that they're always constant. Okay, so at the beginning of the storm, at time 0, there's going to be a lot more water infiltrating down into the soil, but it's decreasing over time. Assuming a constant amount of precipitation, the amount of infiltration decreases over time. And we're going to see the same figure, the same curve on a lot of different figures. Anybody want to take a stab at guessing why does the amount of infiltration decrease over time? Very good. Yeah. So, I mean, when you filled the voids, you know, where's the water going to go? And along those same lines, it's related to that is think about the soil water pressure. You know, when the soil is dry, then the rate that it's sucking the water down from the surface is much higher than once the soil is becoming saturated. So we call this a declining rate of infiltration. And estimating the declining rate of infiltration is what we're going to be doing with the laptops on Tuesday of next week. Is there are a couple of different models that say, well, how long does it actually take before the soil doesn't want to receive any more moisture? You know, trying to estimate the shape of that curve is a really important thing that depends on the soil properties, depends on the rainfall rate, and you know, a variety of other things. So if the water isn't infiltrating, then that means it's staying at the surface. And so the rest of this figure is just talking about some of the other places that the water can go. So of the infiltration, some of it is going into the soil moisture. You know, so some of the water that does get down into the surface is going to be increasing not just the depth of the water table, but also making, in the unsaturated zone, making the water wetter there, but not necessarily saturated. So putting maybe a thicker coating of water along the outside edge of the grains. Some of the moisture is actually going to be causing groundwater flow. So that's the lateral motion of the water towards some outlet. Unsaturated flow is sideways movement of water above the water table. Overland flow is actually the runoff that's on the top surface of a ground surface, you know, whether it's pavement or whether it's grass, but it's not deep enough to be considered channelized. And so overland flow is really shallow sheet flow that moves at a relatively slow velocity. And then channel flow, of course, is moving much more quickly than overland flow ever would. So as time goes on, an increasing amount of the water is in channel flow. At the beginning of the storm, there's no channel flow yet. So all of these other things have to be satisfied before we start seeing channel flow. And channel flow, if we step back away from the science and think in terms of the engineering, that's really, the channel flow is what we're most interested in, because that's what can cause the damage to property. You know, thinking about how the soil grains are increasing their moisture, that's not really like a flooding concern necessarily. It's the channelized flow that is the flooding concern. And so we want to know how quickly, from when the precipitation starts, we start to get to the channel flow. And all of these other factors are going to be affecting how quickly and the amount of channel flow that we see. So if we're trying to reduce peak flows, then what we want to do is maximize the amount of time and the volumes of water for each of these other factors. All right, so remember I said that the ordering of this is kind of, it's hard to know where to begin. We already talked about the zone of saturation. That's where the void space are completely filled. The zone of aeration is above the water table. Atmospheric gases can circulate there. And so the voids, it's not that the voids are completely empty or even that they're partly empty. The voids have something in them. It's either water or gases. And in environmental remediation, there are some techniques that rely on big fans at the surface that actually will pump air down through the subsurface to like ventilate out spilled gasoline, for example, because some environmental pollutants are highly volatile and we can get them to evaporate. So volatile organic compounds circulate through the zone of aeration, and water can evaporate out of the zone of aeration, although it happens pretty slowly. If we can divide the zone of aeration up into some subzones, and closest to the zone of saturation is the capillary zone, closest to the surface is the soil water zone, and then there's this intermediate zone. And so they're shown on this figure, and the amount of water in the zone of aeration decreases the further away we get from the aquifer under steady conditions when it's not raining. I want to jump ahead to a different figure just for a moment before we talk about this infiltrometer. So this is the one I want to show. All right. So here's the surface and here's the zone of saturation. So here's the water table. So below it is the zone of saturation. Above it is the zone of aeration. And so what this figure is showing is that the moisture content is fully saturated at the water table, and if we went below it, it's still saturated. But then as we go up in elevation, then the moisture content is decreasing until we get to some typical moisture content at the ground surface. So the shape of this curve is dependent on the soil characteristics, and this is the capillary zone, where the water is being drawn up higher than it otherwise would if there wasn't any attractive force between the water and the soil grains. The shape of this curve is because of the attractive capillary force. But when it starts to rain at the surface, then this moisture content figure is going to be pushed to the right. So we'll see that in a minute when we look at this same figure under the response of a pulse of infiltration. All right, so one of the ways to measure the capacity for water to infiltrate, a physical measurement of it, is a single ring. This is a single ring infiltrometer, and what it's showing is that you actually put a pool of water at the surface and you measure over time how quickly the water level is decreasing. And so you graph that, and we know that as the water penetrates, it doesn't just go downward, but it also moves sideways as well. And that kind of makes the single ring infiltrometer that we're showing here overestimate the infiltration capacity for water. Because when it's raining, we'd have a really wide pool of water, and we wouldn't be able to have the same sideways movement of water that this is able to take advantage of. So the way around that effect is with a double ring infiltrometer. What you'll do is on this outer ring, you'll have an amount of water that is going to satisfy the sideways movement of water. And so the inner ring, the water level decreasing, is, we hope and assume, just going to be satisfying the downward movement of water through the soil column. And so this is a little bit more accurate way of physically measuring the condition of the water and how quickly it infiltrates through different types of soils. And this is one of the ways that they classify soil types according to the hydrologic soil group that we're most interested in, is actual field measurement of it. Okay, porosity, we've defined the volume of voids relative to the total volume. Soil moisture content can go all the way up to porosity. So during a storm, the water increases from initial water content to saturated in the soil. And so we call that delta theta, how much additional water went into these voids during a storm. And you can see in this figure that some of the space in the void is filled with water and some of the void is air filled. So when there's water coming into a soil volume from above, it's going to be filling in these air-filled void spaces. And the capacity that we've got for additional storage of water is delta theta. It goes from the initial to saturated. Even after it's drained, it has some residual soil moisture content. And so we can calculate the effective saturation by the formula that's shown here. And what it essentially is at any given time, the available moisture that's there relative to the effective porosity. So we'll need to use the effective saturation in some of our calculations later on. There's the formula for it. Who remembers Darcy's law? You've done that before, right? Now, the figure of it here always makes more sense to me when I rotate the sand column sideways. And it's usually presented vertically like this, but it ends up being numerically the same if we have a container of water. Here is one container of water, and we've got water going to a lower elevation pool through this certain area of a soil, and we want to try and talk about, for this delta H, how quickly the water is moving through there. And we use constant surface elevations during the test, and Darcy's law says that the flow rate through this column is proportional to the cross-sectional area that you have the water to flow through it. And we also have to take into account the length that the water is traveling through, because we have friction or resistance to flow through this column. And the longer the column of water, the more the friction is going to be through that matrix. And H1 minus H2 is the driving force. It's the head that drives the flow through the soil column. And so the proportionality factor between these things is the hydraulic conductivity, K. And that's a soil property that characterizes how quickly the water is able to move through it. And depending on the given units, we may need to convert it to meters per second if we want this to end up with, units of volume per time. Sometimes the slope of the water surface, so the difference in height relative to the length, is given the term J here. And we could come up with the flux, which is the overall flow per unit area. So this lowercase q is just kind of like a normalized flow per unit area, the Darcy flux. There's a picture of Darcy. All right, so just to renew our appreciation for Darcy's law, let's do a calculation example here where we've got a fine sand in this column, and we've got the hydraulic conductivity given of 3 meters per day. And so what flow rate Q would you expect through the column if it's given the dimensions that are provided there? All right, so did we get about 5 liters per day for this? Could you do this experiment? Like if I gave you $20 and sent you to Lowe's, could you build something to actually do this test? And think about how would you actually physically do Darcy's law? Like if you had some soil and you wanted to know the hydraulic conductivity of it, I think this is one that actually would be pretty easy to do on the cheap. all you'd need to do is get like a section of pipe, right? Fill the pipe up with soil, cap the pipe on either end, maybe get some buckets, connect the buckets with tubing, and maybe you'd need like a screen so that the sand wasn't washed out of the piping. But this is something that would be pretty easy, I think, to physically replicate. Now, I'm sure that Armfield or somebody out there is selling a contraption that's probably tens of thousands of dollars for the same thing, but I think you could build this experiment for 20 bucks. The tough thing would be what's pictured here. See how there's this little water dripping out of the side? Anybody want to tell me about that? That's a good guess, but that's actually not it. It's like an overflow. It's saying you put in more water than you actually need to go through the column of soil, and so you have like an overflow, kind of like, well, we had something similar to that in the fluids lab when we were doing, I think it's the jet, tracing the trajectory of the water jet. We wanted the height to always be constant, and so we had an overflow there. This is an overflow so that you have constant head, both at the discharge and at the head end of the device. And so I think the tricky thing would be, so you've got these buckets of water, like if you're actually building this, you've got these buckets of water, and you need the water level to stay the same during the test, and then you need to quantify the flow rate as it moves from one bucket to another. So you'd have to have, if the heads are going to be the same, then you'd have to have the water coming out of this bucket, and you see this measured cylinder here. They're saying they're, I guess, doing the stopwatch and the volume accumulation approach to find out the flow rate through there. So you could do it on the cheap. You'd have to be smart about things. The other thing that I think is interesting to consider is that this is in steady conditions. This is once it's reached equilibrium. But if you were going to actually initiate this experiment, when you begin, the soil presumably is dry. And so at first, the water is going to move really fast through that upstream bucket, and it's going to fill the voids very quickly, and in fact, the water maybe is going to be sucking it down. It's going to be more than just the gravitational pressure effect of that upstream bucket. It's actually going to be sucking the water into the soil, but then that would decrease over time as the voids get filled and the soil suction pressure decreases, and so it would eventually reach an equilibrium. And so where we're heading on Tuesday of next week is we're going to be trying to predict how quickly moisture at the surface penetrates down through the soil column. And so this is the curve that you maybe remember I showed you just a few moments ago. It's saying that at the ground surface there's less water in the vadose zone than at the water table. We've got this curve of decreasing water content where it goes all the way to saturation, which is that all the voids are full. But when it starts to rain, now suddenly at the surface you've got full saturation. And so there's some depth underneath the surface that's saturated, and how quickly does that wetting front move down, and what's the shape of that wetting front determines the infiltration rate and therefore the runoff rate. So there are a couple of models that say how quickly that wetting front goes downward and the shape of the curve. All right, but that's all I've got for you today. Let's remind ourselves of these announcements. During we were working the example, I handed out the next homework assignment to you, homework 6, infiltration. So that's due a week from today, and then we've got our exam coming up. So, start cramming all those vocabulary words and refreshing your memory of the terminology. All right, have a great day.